Hello friends, today we are starting with a new series on statistical mechanics. In the first episode, we will be dealing with a general introduction to the statistical mechanics. Statistical mechanics is one of the major and fundamental topics in physics. It touches almost every aspect of investigations within the field of physics, starting from the very experimental fields to the theoretical investigations with which we try to understand the nature and the natural phenomena. If we search for a definition of the statistical mechanics, it basically try to explain or make a connection between the macroscopical physical parameters of the so-called thermodynamical systems in terms of the microscopical constituents. Now, a bigger question which one needs to look into is why statistical mechanics, or when did the statistical mechanics started or it's begun. Now, we know that if we look into the history of science, thermodynamics played a bigger role. Even in our day to day life, these days even, the thermodynamics plays a major role. In the growth of thermodynamics, the laws of thermodynamics played a bigger role. The evolution of the laws of thermodynamics is very much connected to the evolution of science. So, basically the laws of thermodynamics, as we know, is trying to make a connection between certain macroscopic parameters such as pressure, volume, temperature, internal energy, which many times we designate using the denotation U, and all these terms are connected to one of the major other thermodynamic parameter which we call as the entropy. So, these laws of thermodynamics did really helped us to understand the natural phenomena in a bigger form, and not only that, these laws were later applied for the development of various technological applications. For example, our Carnot's engine. So, is a simple application of the thermodynamical laws. But in the history of science, there came a phase in which for the further development of the thermodynamics or for further extending the thermodynamical phenomena, we needed to have a fundamental understanding of the thermodynamical behavior. So, the science always tries to model any physical system or the natural systems which comes into its purview. So, in that phase, I believe that the kinetic theory of gases played a major role. So, kinetic theory of gases basically connected the thermodynamical parameters with some molecular dynamics. So, but that was a preliminary attempt. The beauty of the kinetic theory of gases is that it could almost explain all the thermodynamical behaviors in a satisfactory way. But for the further evolution of thermodynamics, especially when the classical and the quantum mechanical formulations improved, many of the kinetic theory of gas the speculations made by the kinetic theory of gases were not satisfactory for the explanation of all the thermodynamical phenomena. So, by 1850s, by the fabulous work of various scientists like Carnot, Joule, Clausius or Kelvin, thermodynamics had become a stable field of physics. But still it was believed that the kinetic theory of gases which tried to explain the thermodynamics was rather a speculation, and it was not good for making any major formulations for the development of thermodynamics. But this phenomenon, this phase got changed with the introduction of the H theorem by Boltzmann. With the theorem of Boltzmann, almost it happened that the kinetic theory of gases got replaced by the ensemble theory. So, then later it got developed in the classical way, and then in between by the beginning of the 19th century the quantum mechanics came. So, naturally all these theorems got tuned itself to the quantum mechanical models and the formula and the theorems, and then the statistical mechanics got slowly developed. So, in short, we are trying to understand a physical system which is made up of the molecules by combining two areas. One is the statistics, many times which we identify as a part of logics, and then the mechanics. So, statistics and the mechanics were combined together to derive a new branch of physics, which was the statistical mechanics. The statistical mechanics will not give you a life history of a molecule. That is one important thing, because we are not, as we know, even in 1 mole of gas has got 10 raised to 23 particles, which means that it will be really cumbersome, or it will be really foolish for a scientist to track the dynamics of each and every particle in that, even in 1 mole of system. So, we need some kind of a model which takes into account its statistical behavior or its probabilistic behavior of the particles. The statistical mechanics and its theorems gives a excellent door into observing such kind of systems from a theoretical perspective. And the best part is that the statistical mechanics did explain all the natural phenomena which the physics is trying to explain. So, many times people think that it is an extension of the classical mechanics or the quantum mechanics. The matter is that statistical mechanics does use the concepts of classical mechanics and the quantum mechanics, but the aim is to understand the dynamics of the molecules which results in a behavior of a particle. For example, the behavior of electrons. So, the behavior of electrons in a system cannot be understood by any if we go into the molecular level. Instead, we need to go into a statistical regime. Fermi introduced the concept of Fermi statistics. So, based on the Fermi statistics, now we know how the electron will behave if we vary the temperature or if we vary the physical parameters. How does the electron energy gets distributed based on the changes in its physical inputs. So, that is one of the outputs of the statistical mechanics. So, the classical we started with the classical statistical mechanics by the work of none other but Maxwell. Many times we identify him with electrodynamics, but Maxwell has done some excellent work in the field of statistical mechanics, especially to explain the electrodynamical systems. Then the Boltzmann and Gibbs, also Fowler. So, these scientists basically use the classical concepts for the development of the statistical mechanics. So, now we will try to see two fundamental parameters which comes across any description of statistical mechanics systems. The terms are macrostate and the microstate. So, as I told you in the beginning, the thermodynamical systems are more about observing or trying to explain the macroscopic phenomena. But then we have certain microscopic quantities which underlie in the evolution of the macroscopic or the dynamics of this macroscopic parameters. So, basically these two terms are trying to explain such a situation. Let me try to demonstrate the macro state and the micro state with an example, because the exact understanding of the terminology macro state and micro state is very critical for the understanding of this whole episode of this whole series on the statistical mechanics. So, the typical example with which we try to explain is based on the tossing of coins. So, imagine that you have a coin and you try to toss it 4 times simultaneously. So, now if I ask you what are the kind of possibilities which comes out of that tossing. So, you know that in a coin you have head and the tail. So, after 4 tossing, one of the possibilities that I might be getting 4 heads. Another possibility is that I might be getting 3 head and 1 tail. The third possibility is that I may get 2 heads and 2 tails. I might be getting 1 head and 3 tail, or another possibility is that I might be getting 4 tails. So, these are the 5 possibilities which one can think when one is tossing a coin 4 times simultaneously. So, in a way these 5 possibilities actually define the possible number of macro states in the system. Now, if we go into this system, this demonstrative case in a more deeper manner, I can write it like this: H, 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 which means that in all the tossing, every time I toss, I end up getting heads only. But when it comes to the 3 head 1 tail case, I might be getting it in different manners, like H, 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 T, or I can get H, H, T, H, or H, T, H, H, or T, H, H, H. So, these are the 4 possibilities with which I can get 3 head 1 tail. So, correspondingly you yourself can for example, for this one I can write HHTT, right. For 2H2T I can write TT HH, HT HT, TH TH, HTT H, TH H T. So 3H1T I can get it in 4 different manners. 2H2T I can get it in 6 different manners, and correspondingly for the 1H3T again, if you can write it yourself, I will be able to get this 1H3T configuration in 4 different manners, and 4T again in only 1 manner. So, see, for a outside for a person standing outside the room in which this event of tossing the coin was happening, for him all these events will look the same. If his question is that, okay, what was the result, then your answer would be, so we got 3 heads and 1 tail. So, for an outside the room person, for a macroscopic world, all these possibilities will sum up into one single result, or all these 4 micro states will lead into one macro state. So, all these things, so I can write it here, this represents the macro state and this represents the micro states. Okay. So, which means what? How many macro states in total? So, we have 5 macro states in total. 5 macro states in total. And how many micro states? So, I have written only the number of micro states for the initial 3. So, if we count that, there will be 16 micro states corresponding to 5 macro states. So, this is how we explain a connection between the macro state and the micro state. So, micro state basically defines different manners or different ways in which one can achieve a macro state. Now, your question could be that is any micro state being preferred over another micro state? The answer is that according to the statistical mechanics, we have the postulate of a priori possibilities, a priori probabilities, which states that every micro state is equally probable for a macro state. So this postulate tells that for a particular macro state, there is no preference for any micro state. Now, the question is that is there any number which connects the number of micro states, which is very critical in the understanding of statistical mechanics, which we define it by the term omega. So, basically omega gives the number of ways in which one can achieve or the number of micro states possible in a micro state. We always try to explain or write it in terms of the macroscopic parameters n, v and the e. But let me tell you that depending on the kind of parameter which is changing in an experiment, we can always mention it in terms of one single parameter also. So, in general it means that the omega, which represents the number of microstates possible in a macro state, we can represent it as omega of NVE, and this omega is otherwise known as the statistical weight or thermodynamic probability. So, depending on the kind of literature or the textbook which we use, the terms like a statistical weight or thermodynamic probability can be used to express the value of omega. Other than being a number, this term suggests that it is also a probability, which means that see in the case of our of this experiment with our coin tossing, if I ask you which macro state is the most probable, your answer will be 2H2T. Why? Because it has got 6 different ways in which it has achieved, which means that is in 16 micro states or 16 different probabilities with which we achieved the macro states, 6 of them belong to 2H2T, which means that the 2H2T can be identified as the most probable state, or we call it as the equilibrium state. So, 2H2T here is known as the equilibrium state, which means what? Which means that if we allow the system to leave, if we leave the system to itself, after some time the system will try to achieve the so called equilibrium state. So, in the statistical mechanics, so in the example which we discussed about, which is the coin, that is only about 6, the one coin tossing 4 times. But here in the statistical mechanics, we are seeing an entirely different perspective. See, the 1 mole of your substance contains 10 raised to 23 kind of number of particles. So, it works in an entirely different regime, there in the case in which we are unlike the case of the coin tossing, when it comes to the regime of the statistical mechanics or the physical phenomenons, the numbers are huge. Therefore, the concept of equilibrium state is very important, especially in this series of lecture we will be mainly dealing with equilibrium systems, which means that these systems will achieve an equilibrium at some point of time. So, this distribution models which we will be discussing in this series will be trying to explain it based on the distributions which it achieve after equilibrium. So, there is a different class of statistical mechanics concept based on the non-equilibrium states, which we will not be discussing in this series of courses, because that is an advanced course material. We have defined the macro state and the micro state. Now, for every discussion on the physics or the physical within the physical sciences, we try to invoke the theorems of quantum mechanics. So, if I talk in terms of the quantum mechanics, we have the concept of Schrodinger equation, Hi is equal to E psi. So, here H represents the Hamiltonian, psi represents the wave function, E represents the eigenvalue and so on. So, this equation is very critical for any discussion on the physics. So, now if I invoke this concept of macro state and micro state into this Schrodinger equation, for a particular microstate will always have a different wave function. For example, psi of R1, R2 up to Rn represents one of the microstates which will have a corresponding eigenvalue. So, this wave function basically represents one microstate, and if I have another microstate, it will have a different kind of wave function or different wave function rather than this one. So, each microstate can be represented in terms of a particular wave function, and therefore, you know that the wave function and the psi squared will give you a probability, right. So, which means that each microstate will definitely have a probability. So, all the concept of macrostate and microstate is equally valid for a classical situation like the tossing of coins which we talked about, and it can be extended to the quantum mechanical concepts by using the Schrodinger equations. So, after few episodes, we will definitely delve ourselves into the regime of the quantum statistics, and you know that the Fermi-Dirac and the Bose-Einstein statistics, which have decided or which are very critical for the present day investigations of any material science investigations, are all based on the quantum mechanical investigations. But at the same time, we will be starting with the Maxwell-Boltzmann statistics and the classical discussions in our initial series of lectures. So, that was a general introduction to the statistical mechanics. So, now we have reached the end of this first episode. In this episode, we have seen one, we have put a general introduction to the topic of statistical mechanics, and then we saw the kind of evolution from the field of thermodynamics to the concepts of statistical mechanics. Another thing which we saw was two critical terms related to the discussions of statistical mechanics, which was the microstate and the macrostate. And also we introduced the concept of a priori probabilities, the postulate of a priori probabilities, and we understood these concepts based on the we demonstrated these concepts based on a simple example of tossing of coins. In the coming episode, we will try to make a relation between statistical mechanics and thermodynamics, which was again proposed by Boltzmann. So, we will continue with our discussion in the next episode. Till then, bye. Thank you.